Good morning, all of you. In this session, I am going to explain about free body diagrams for friction. You can observe this diagram. Okay. Before going to the free body diagrams, first you have to know the fundamental about action and reaction. From the Newton's third law of motion, we know that to every action there is equal and opposite reaction. Hence, reaction is always equal and opposite to the action. Here, capital R is the reaction force. W is the self weight of your body. Capital P is the applied force, externally applied force. F is frictional force. F equal to mu into R. Let's consider a horizontal rough surface. For smooth surface, there is no friction. Okay, please remember, for smooth surfaces, there is no friction. Okay, for rough surfaces, only you have to consider friction. Okay, so here I consider a horizontal rough surface. Okay, now I am placing a roller of weight W. Okay, now I am applying a force P to move this roller in right side direction. Okay, now here you can observe the self weight of a roller is W. Okay, so this W force always acts vertically downwards. Okay, already we know that the self weight of any body acts vertically downwards. Self weight of any body acts vertically downwards. Okay, now this W is the action. Okay, W self weight is the action. Now you have to draw a reaction force. Okay, here this point is the contact point between horizontal surface and roller. Okay, at the point of contact there is a opposite reaction. Okay, so here this is the reaction force. Always reaction force perpendicular to the surface. Okay, here this is the horizontal surface or support. You have to draw a perpendicular line. Okay, so reaction force always makes an angle 90 degrees with respect to the support. Okay, so it is very important. So this is the reaction. Okay, W is the action, capital R is the reaction. Now here we are applying a externally applied force P with an angle theta with respect to the x-axis like this. Okay, when you are applying the externally applied force, then this roller will move right side direction. Okay, for rough surfaces you have to consider frictional force. Okay, frictional force always acts at point of contact. Okay, so you have to consider a frictional force at point of contact like this, and this frictional force always acts perpendicular to the direction of motion. Okay, here right side direction is the direction of motion, so you have to consider opposite direction for frictional force. Here W is the frictional force. F equal to mu into R. Here mu is the coefficient of friction. Okay, mu is the coefficient of friction. Capital R is the normal reaction. Okay, so always you have to consider a frictional force opposite to the direction of motion. Okay, now I am showing the free body diagram for this figure. This is a horizontal line. Okay, here you have to consider this vertical weight W, self weight, as it is, and you have to draw a normal reaction vertical upwards like this. Okay, so this normal reaction makes 90 degrees with respect to the horizontal plane. Okay, now you have to draw a externally applied force P. Okay, it makes an angle theta with respect to the x-axis. Now then after you have to draw a frictional force F equal to mu r, horizontal force. Okay, here the frictional force always parallel to the surface. Okay, so frictional force always acts parallel to the surface. So you have to draw a horizontal frictional force. Okay, the direction of frictional force always depends upon the direction of motion of the body. Okay, the frictional force always acts opposite to the direction of motion. Okay, so this is the final free body diagram for this figure. Okay, this is the example 1. Now coming to the another example. Now this is a rough horizontal plane. Now I am considering a rectangular block of weight W. Okay, now W is the action of the body. Okay, this self weight W always acts vertically downwards. Already we know that. Okay, self weight always acts vertically downwards. Then after you have to draw a normal reaction force. Okay, here this is the point of contact. Okay, so you have to draw a perpendicular line with respect to the support. Okay, this is the normal reaction. Normal reaction always makes an angle 90 degrees with respect to the support. Okay, so reaction force always perpendicular to the support. Okay, this is the horizontal support, so you have to draw a perpendicular reaction force, or normal reaction force. Now this is the vertical self weight, this is the horizontal reaction. Now I am applying a force, external force P, to move this object. Okay, to pull this block you have to apply an external force. That's why I am applying a external force like this. Then the direction of motion is towards right. Okay, so you have to consider a frictional force opposite to the direction of motion. Okay, always you have to consider frictional force opposite to the direction of motion. Okay, here this is the applied force, this is the frictional force. Okay, this is the direction of motion. Okay, now you have to draw this external force P and the frictional force F here. Okay, this is the horizontal friction force, this is the applied force. Okay, please remember, always you have to draw a frictional force parallel to the support, Okay, frictional force always acts parallel to the support. Okay, and the normal reaction always acts perpendicular to the support. Okay, this is very important. So here W is the self weight always acts vertically downwards, and reaction force always acts perpendicular to the support. Okay, please wait. Okay, so this is the example number 2. Now coming to the another example. Now I am considering a vertical rough surface. Okay, then A block of weight W slides vertically downwards without any external force. Okay. Now you have to consider self weight vertically downwards. Always you have to consider self weight vertically downwards. Okay. Now this is the vertical support. So you have to draw a perpendicular reaction force at the point of contact. So here this support, you have to draw a perpendicular reaction force with respect to the support. Always reaction force makes an angle 90 degrees with respect to the support. Okay, here the support is vertical, so you have to draw a horizontal reaction. Okay, so this is a x-axis, this is y-axis. So first of all, you have to draw a self weight W vertically downwards. Okay, then after you have to draw a normal reaction force R like this. Okay, now the direction of this block is vertically downwards. Okay, for a freely falling body, you have to consider the direction of motion is downward. Okay, so if the direction of motion is vertically downwards, then you have to consider a frictional force opposite to the direction of motion. Okay, here the direction of motion is downward, then you have to consider the direction of motion, then you have to consider frictional force opposite to the motion, direction of motion. So this is the frictional force. Always frictional force acts parallel to the support. Okay, so you have to draw this frictional force on y-axis for this condition. Okay, so this is the final free body diagram for this condition. Okay, now the last condition is inclined support. Okay, this is a inclined rough surface. I am placing a block of weight W on the inclined plane. Okay, this inclined plane makes an angle theta with respect to the horizontal line. Okay, so this theta is called angle of repose. Okay, angle of repose. Here the theta is called angle of repose. Now I am drawing the forces. This self weight W always acts vertically downwards. Okay, you have to draw a vertical line for indicating the self weight of the block. Okay, now you have to draw a normal reaction. Normal reaction always acts perpendicular to the support. So you have to draw a perpendicular line with respect to the support. Okay, this reaction force makes an angle 90 degrees with respect to the support. Okay, here the support is inclined with respect to the horizontal plane. Okay, here this support makes an angle theta with respect to the horizontal plane. Okay, so first this is the horizontal axis, this is the reaction force. Okay, this reaction force makes an angle theta with respect to the y-axis. Okay, this reaction force makes an angle theta with respect to the vertical axis. From you can observe the total angle is 180 degrees, the right side angle is 90 degrees, and the left side angle is theta plus 90 minus theta. Okay, so total angle is 180 degrees. Now if you are drawing a vertical axis here, then the angle is theta. Okay, now if you are considering a freely falling body or a freely moving body, then the direction of motion is downwards. Okay, there is no external forces acting on the block. That means, okay, there is no applied force P. Now the direction of motion is like this. Okay, then you have to draw, then you have to consider a opposite frictional force. Okay, so the frictional force is like this. Okay, this frictional force is opposite to the direction of motion. Okay, the direction of motion is downwards, so you have to consider upwards frictional force. Always frictional force acts parallel to the support, parallel to the support. So now you have to draw this frictional force here. It makes an angle theta with respect to the horizontal axis. Okay, this frictional force makes an angle theta with respect to the horizontal axis. Okay, this is the final free body diagram for this inclined plane problem. Okay, now same, I am considering same condition. Okay, this is the self weight, this is the reaction force. This reaction force makes an angle 90 degrees with respect to the support. Okay, okay, now if you are applying a force in upward direction, okay, if you want to pull this block in upward direction, that means we are applying a external force P on the block. Okay, then the direction of motion is upward. Okay, if the direction of motion is upward, then you have to consider a frictional force downward direction. Okay, so frictional force always acts parallel to the support. Okay, frictional force always acts parallel to the support. Okay, F equal to mu r is the frictional force, and this is the applied force. Okay, now you have to draw these two forces here. This is the frictional force mu r, and it makes an angle theta with respect to the x-axis. Okay, this frictional force makes an angle theta with respect to the horizontal, so you have to consider theta angle with respect to the horizontal, and this applied force is parallel to the inclined plane. Okay, you can observe here this applied force is parallel to the inclined plane, so the angle of this applied force also theta with respect to the horizontal. Okay, this is the final free body diagram for this condition. Okay, now I am going to explain a simple problem on this condition. Okay, here this is a horizontal rough surface. This is a block of weight 100 newtons. Now I am applying a pull force, horizontal pull force, P equals 16 newtons. Then you have to determine a coefficient of friction mu, between horizontal plane and block. The question is, a body of weight 100 newtons is placed on a rough horizontal plane. Determine the coefficient of friction if a horizontal force of 16 newtons just causes the body to slide over the horizontal plane. Okay, this is the question. From the given question, first you have to identify the given data. Okay, here a body of weight 100 newtons, that means self weight W equal to 100 newtons. is placed on a rough horizontal plane. So for rough planes, you have to consider frictional force. Okay. For smooth planes, don't consider friction. Okay. Only you have to consider for rough surfaces. Okay. So the given problem is rough plane. So you have to consider a friction. So F is the friction. Determine the coefficient of friction. That means mu. Okay, you have to determine a value of mu, coefficient of friction. Here the horizontal applied force is 60 newtons. Okay, so solution given data is self weight of a body W equal to 100 newtons and horizontal applied force P equal to 60 newtons. Okay, now let capital R is the normal reaction and coefficient of friction equal to mu, frictional force equal to F equal to mu R. Okay, by using these two values W and P, you have to determine reaction force, coefficient of friction, and frictional force. Okay. Okay. First of all, you have to draw a free body diagram for this problem. Okay, this is the given condition. Here W is the self weight. The self weight of a body always acts vertically downwards. Okay, W equal to 100 newtons. Self weight always acts vertically downwards. Now you have to consider a normal reaction at the point of contact. Here, this is the support, horizontal support. So you have to consider a perpendicular reaction or normal reaction. The normal reaction force always makes an angle 90 degrees with respect to the support. Here the support is horizontal. So you have to consider a vertical reaction force. Okay. Now, this is the free body diagram for these two forces. Now we are applying the externally applied force P equals 60 newtons. This is a horizontal pull force. Okay, so you have to consider this pull force as it is. By applying this full force, the direction of motion is like this. Okay, now the frictional force F equal to mu R acts parallel to the support, and this value is opposite to the direction of motion. Okay, here the direction of motion is right side, so you have to draw a opposite direction for frictional force. Okay, this frictional force always parallel to the support. Here the support is horizontal, so you have to consider a horizontal frictional force. Okay, now this is the applied force P. Okay, now you have to draw these two forces here. This is a frictional force F equal to mu R in left side direction, and this is the applied force P in right side direction. Okay, so this is the final free body diagram for this problem. Okay, self weight W always acts vertically downwards, and reaction force always makes an angle 90 degrees with respect to the support. Okay, and the frictional force is always opposite to the direction of motion. Okay, here the direction of motion is right side, so you have to consider opposite direction for frictional force, and this frictional force always acts parallel to the support. It is very important. Okay, so these four forces are acting at a common point like this. Now consider a free body diagram as it is. Okay, this is the free body diagram for this problem. Now from this diagram you have to determine the value of mu. that is coefficient of friction, and normal reaction force R. Okay, these two are the unknown values. So for determining the unknown values, you have to consider sum of horizontal forces and sum of vertical forces. From equilibrium conditions, sum of all vertical forces equal to 0. Sum of all vertical forces equal to 0. Okay. So here, these two are the vertical forces. Vertical forces always lies on y-axis. Okay, this is the y-axis. So these two are the vertical components. For upward direction, you have to consider positive sign. For downward direction, you have to consider negative sign. Okay. For upward direction, positive sign. For downward direction, you have to consider negative sign. Okay. So in similar way, for left side direction, you have to consider negative sign. For right side direction, you have to consider positive sign. Okay. So from this diagram, W acts vertically downwards. So vertically downwards, you have to consider negative sign minus W, and this reaction force acts vertically upwards. For upward direction, you have to consider positive sign. So plus R minus W equal to 0. Sum of all vertical forces equal to 0. Okay. Now from this equation, capital R equal to W. Now here W equal to 100 newtons. Okay. So the reaction force capital R equal to 100 newtons. Okay. We got a unknown value. Reaction force R equal to 100 newtons. Okay. In similar way, sum of all horizontal forces equal to 0. Sum of all horizontal forces equal to 0. That is Fx equal to 0. Here F equal to mu R and P equal to 16 newtons. These two are the horizontal forces. Horizontal forces lies on x-axis. Okay. So for right side direction, you have to consider positive sign. For left side direction, you have to consider minus sign. So this value is positive, plus P minus mu R. Okay. F equal to mu R. F is the frictional force. This frictional force is equal to the moment of coefficient of friction and normal reaction. Okay. So this value is minus mu R equal to 0. Okay. Now P equal to mu R. Already we know the value of P. P equal to 60 newtons. So the value of mu R equal to 60 newtons. Here the mu R equal to F, that is frictional force. Frictional force F equal to mu R equal to 60 newtons. Okay. From this equation, you have to find out the value of mu. Okay. From mu R equal to P equation. Okay. The coefficient of friction mu equal to P by R. Okay. From this relation, you have to find out the value of mu. Coefficient of friction between horizontal plane and block. Okay. So mu equal to P by R. Now here P equals 16 newtons and R equal to 100 newtons. Okay. So 60 by 100 equal to mu equal to 0.6. Okay. This is the value of coefficient of friction. Already we know that coefficient of friction has no units. Okay. So no units for coefficient of friction. Okay. Here the reaction force has units Newton. Okay. Here you can observe coefficient of friction equal to ratio of externally applied force divided by reaction force. Both are having same units. Okay. Therefore, the coefficient of friction has no units. Okay. No units for mu. Okay. The value of mu is 0.6. This is the answer for this problem. Okay. Now I am repeating the free body diagrams again. Please listen carefully. Okay, self weight always acts vertical downwards. Reaction force makes an angle 90 degrees with respect to the horizontal plane. Okay, this is the applied force. Here the direction of motion is right side. Then you have to consider opposite direction for a friction. Okay, this frictional force always acts parallel to the support. Okay, this is the free body diagram for this condition. Okay, in similar way. Okay, here this is the another condition. Here this self weight W acts always vertically downwards. This is the reaction force, makes an angle 90 degrees with respect to the support. Okay, here this is a force, actional applied force P. Then the direction of motion is towards the right. Okay, then you have to consider frictional force towards left. Okay, frictional force always acts opposite to the direction of motion. Okay, and this is the applied force. This is the free body diagram. Okay, for this condition. Now here you can observe this is a vertical support. Okay, here also the self weight W acts vertically downwards, and the normal reaction makes an angle 90 degrees with respect to support. Here the support is vertical, so you have to consider horizontal reaction force. Okay, now this is a freely falling body. Okay, this is a freely falling body, so the direction of motion is vertically downwards. Then the frictional force is vertically upwards. Okay, this is the free body diagram for this problem. This is a rough inclined plane. This inclined plane makes an angle theta with respect to the horizontal. Okay, this angle theta is called angle of repose. Okay, here in this condition also this self weight W acts vertically downwards. Okay, and this is the reaction force makes an angle 90 degrees with respect to the inclined support. Okay, so this is a reference horizontal line. Okay, this is a reference horizontal line. This is a reaction force. This is a vertically downward self weight force. Okay, this reaction force makes an angle theta with respect to the vertical. Okay, always reaction force makes an angle theta with respect to the vertical. Okay, this theta is called angle of repose. Okay, now the direction of motion is vertical. The direction of motion is downwards. Then the frictional force is upwards. Okay, so this is the direction of a frictional force. This frictional force acts parallel to the support and opposite to the direction of motion. This frictional force makes an angle theta with respect to the horizontal. Okay, now same condition. Okay, now if we are applying a actional force like this, okay, if you want to pull this block in upward direction, then the then the direction of motion is upward. Then you have to consider a frictional force downward. Okay, so always the frictional force acts opposite to the direction of motion and parallel to the support. Okay, so this is the applied force, this is the frictional force. Here this is the direction of motion. Okay, this frictional force makes an angle theta with respect to the horizontal. Okay, and this applied force also parallel to the inclined plane. Okay, this force also makes an angle theta with respect to the horizontal. Okay, this is the free body diagram for this condition. Okay, okay, in next class I will explain more problems on these conditions.